So, good morning, everyone. Hope you enjoyed the keynote. As part of my day job, I've analyzed hundreds of different code bases. Many of them open source, but also a lot of proprietary and commercial code bases. And today I want to share some of my observations with you, because there are some patterns that I see recur over and over again, and those patterns are independent of programming language or technology. And I want to do this in a different way, because I'm pretty sure that we as an industry, we know what good code looks like. We know about the importance of naming, testability, cohesion, the solid principles, and all that other stuff. So today, I want to go beyond that. And my starting point is going to be data and human behavior. Isn't it fascinating that data analysis today is mainstream? And the rise of machine learning has taught us how to find patterns in complex phenomena. And yet, we developers, we have never really taken those techniques and turned them on ourselves, to understand our own behavior in code, and to uncover patterns in how our systems grow. So that's what I want to do today. And I'm going to show you how that data help us make better decisions. Decisions that guide us towards maintainable code bases. So our first step on this journey is to find some behavioral data on us as software developers. The good news are that you all already have all the data you need. We're just not used to think about it that way. I'm talking about our version control data. Our version control data is a perfect behavioral log of how we as developers have interacted with the code base. Each time we do a commit, our version control data records not only who did the commit, which is social data, it also records when, which gives us a time dimension to our code base. And most importantly, it records where in the code that change took place. So let's dive into version control data and see how it can help us. And let's start with my first observation, which is that maintainable code goes way beyond technology. And we developers, we tend to be pretty good on the technical side, but I've seen that we often miss the social implications of our designs. And this is important. Have a look at this picture. This is what pretty much every system I worked with over the past 10 years have looked like. We have a number of big subsystems that we somehow integrate and let them exchange information. And of course, at one end, we have a big database. Now, each one of those subsystems can be fairly large. They can consist of hundreds of thousands, sometimes even million lines of code. And the scale of that alone makes it pretty hard to reason about. There are few people in the world who can keep a million lines of code in their head. But the challenge here is not just about size and scale, because today's systems tend to be developed in multiple different languages, targeting different platforms. And of course, today's systems are developed by multiple programmers organized into multiple teams. And that leaves everyone with their own view of how the software looks. No one has a holistic picture. But this is not just about technology, because code bases that look like this tend to come with an organization that looks like that. So our challenge as developers is to strike this balance between our technical and social organizational challenges. And this is a hard problem. But it's a problem that we can simplify by understanding the next point. My next point is that when it comes to maintainable code, all code is equal, but some code is more equal than others. And to explain what I mean about this, we need to take a different view. We need to take an evolutionary view of our code base. Here's our starting point. Please have a look at the following graphs. All of them show exactly the same data. On the x-axis, you have each file in your code base. And those files are sorted according to the change frequency. That is, how many commits, how many changes have you done that impacts that particular file? And the number of changes is what you see on the y-axis. Now, the fascinating thing here is that this data is from 3 radically different systems, implemented in different languages, developed by different organizations, and they have a completely different lifetime span. Yet, they all show exactly the same pattern. They show a power law distribution. And this is something I found in virtually every single code base that I've analyzed. And what this means to you is that in your typical code base, most of your development effort tends to be in a relatively small part of the code. Most of your code is here in the long tail, which means it's code that's rarely, if ever, touched. And this is important because it gives us a tool to prioritize. Using this knowledge, this information, we can actually focus our improvements on the parts of the code that really matters for our productivity. And we're virtually free to ignore the rest, at least for now. And this is a good starting point, but we need to do even better. And to explain how, I need to take a risk. Yeah, that's right. I need to put up a slide, and I think this is the point in the presentation where you will all vehemently disagree with me. But I need to take that risk. It's for the greater good, I promise you. I have found that when it comes to maintainable code, code complexity isn't the problem. We developers, we're conditioned to despise bad code. We have learned that we need to refactor and improve bad code as we see it. And we have learned that we need to keep our code clean and nice all the time, because that's the fastest way forward. The problem I have with that is that it's just not true. And the graphs on the previous page indicate why that may be the case. At the same time, we obviously cannot discard code complexity entirely. We just need to find out when it matters and when it doesn't. And this is a problem I've been struggling with for years. So please, let me share a little story with you. This is something that happened like 5 or 6 years ago. At that time, that was in my previous life as a software consultant. And I worked on a fairly large development project. We were like 50, 60 people collaborating. And we had a lot of code. And our productivity wasn't as good as we would like it to be. So we wanted to do some improvements. And the way we prioritized those improvements was that we brought in a complexity metrics tool. And this was a kind of tool who could measure something called technical depth. So what we did was we basically took this tool, we threw it at our code base, and out came a prioritized list of every module in our system, ranked on the technical depth of that module. The interesting thing here was that there was a clear number one candidate. There was one part of the code that seems to be in much worse shape than the rest of it. However, when we started to investigate that code, it turned out that that code had been stable for 3 years. It worked wonderfully in production. We never had to touch it. So what could we expect to gain by improving that code? If you ask me, absolutely nothing. To me, it's just a big risk to touch something like that. So we need some other approach. And at the same time I worked on this project, I was in the middle of my psychology studies at the university, and I took a course in forensic psychology. And I'm pretty sure that forensics has a lot to offer to us software developers. The whole mindset is just right. It's just what we need. And there was one technique in particular that I would like to show you. This is a technique called geographical offender profiling. Geographical offender profiling is about finding serial offenders. So I want to show you a case study from the real world. So what you see here is a map over a city, a map over London. And you see that there are a number of green dots. Each one of those dots represents a crime scene. We have 56 different crime scenes that we have managed to link to the same offender. Now, how do we know it's the same offender? Well, perhaps we have hard evidence like DNA or fingerprints, or it may just be that the crimes exhibit the same modus operandi, the same method of operation, so we're able to link them to the same offender. Now, what you do in a geographical offender profile is that you calculate a probability surface. And that probability surface is based on a mathematical weighting of the distribution of those crimes. But in turn, we weight that model with our knowledge of human psychology and human behavior. When we do that, we end up with a central spot here, the red area here. That's something that's called a hotspot. And that's the most probable home location of the offender. And according to the research, there's a 70% chance that our offender will have his home base there. Now, the reason I think this applies so well to code is if we take a step back and consider what we've actually done. We have taken a potentially vast geographical area and narrowed it down to much smaller part. A much smaller part where we can now focus our human expertise and still be pretty sure that we catch the offender. So what if we could do this in code? What if we could take our million lines of code and narrow them down to a few hotspots and know that if we focus improvements there, we get a real return on that investment? Let's see how a geographical offender profile of a code base looks like. So what you see here is approximately 300,000 lines of code. And this data is built up by geographical patterns, but not of criminals, but of programmers. So this is data mined from our version control data. We have approximately 2,400 commits here. And by identifying patterns in those commits, we're able to calculate the probability surface. And using that probability surface, we're able to detect the most probable maintenance savings in that code. Now, I'm going to walk you through that visualization, but before I do that, I just want to point out that the hotspot analysis in code is actually a social analysis, because this data is built up by calculating the contributions of all contributing authors. So you can view each commit that you do like a vote for the relative importance of that code. This is about the collective intelligence. Now, what you see here? Well, you see a number of large blue circles, right? With smaller blue circles inside them. Each one of those circles represents a folder or directory in your codebase. So this is a hierarchical visualization that follows the folder structure of your code. And if you have large-scale visualizations, I also think it's important that they are interactive so that you can zoom in and out to the level of data of interest. And if you zoom in on one of those folders, you will see that each file in your codebase is visualized as a circle. And you will see that the circles have different size. That's because size is used to represent the code complexity of the underlying code. Now, how do you measure code complexity? Well, our industry, we have a lot of different ways of doing that. You may be familiar with things like McCabe's zygomatic complexity or Halstead's volume metrics. We have a bunch of different metrics, and what all of them have in common is that they are equally bad. So I tend to pick the simplest thing that could possibly work, which in this case turns out to be the number of lines of code. Yet it's a lousy metric, but it's just as good as the other ones. This is all about probabilities, remember. However, I also told you a while ago that code complexity alone is never a problem. So we need something more. We need to find out if we actually work in that part of the code or not. And this is data that we mine out of our version control system. And we use color to represent the change frequency of each part of the code. So the more red, the more opaque a circle, the more commits you have done in that code. And the interesting thing is, of course, when you combine these two dimensions, because now we're able to detect complicated code that you also have to work with often. I want to show you a real-world case study on hotspot analysis. And I want to have a look at the Roslyn project. So how many of you are familiar with Roslyn? Oh, a lot of you, like half of you, great. So Roslyn is like Microsoft's open source flagship product. And Roslyn is a compiler platform. And the cool thing with Roslyn is that it includes two compilers itself. It includes the C# compiler written in C# and the Visual Basic compiler written in Visual Basic. So this is a polyglot code base. If you look at the top hotspots in Roslyn right now, you will see that the top hotspot is something called command line tests written in C#. Another top hotspot is called command line tests and written in Visual Basic. I wonder if there's some kind of relationship between those two. In a few minutes, we're going to learn a technique that helps us answer that question. But before we go there, I just want to point out that those hotspots, they look tiny on screen, even on this big screen, right? That's just because the scale of Roslyn. Roslyn is huge. So this is almost 4 million lines of code. And each one of those hotspots is a file with 7,000 lines of code. And I would like to argue that if you have a test called command line tests, and it consists of 7,000 lines of code, well, perhaps that isn't a good unit of test. And what I would do in this case is that I would investigate the actual responsibilities within that test case and start to split it into smaller test suites based on behavior. So I would have one test suite for testing the parsing behavior, one for validation, one for diagnostics, and so on. And if you do a refactoring like that, not only will each part become easier to understand in isolation, it also gives you an entirely new context. Because if you follow up with a hotspot analysis at a later date, you're able to detect and see which part of your solutions do you manage to stabilize and which parts keep changing all the time. So cohesion is actually a tool that helps us understand the evolution of our code too. Another observation I did here was that you saw those 2 hotspots. They were in the test code, right? And that's something I find over and over again. The worst code tends to be in the test code. And I think that the main reason is because we developers, we tend to make a mental divide. On one hand, we have the application code, and then we know it's vital, it's important that we keep it clean and easy to understand and maintain. And on the other hand, we have the test code. And most of the time, we're happy if we get around to write any of it at all. And I think this is a dangerous fallacy because from a maintenance perspective, there's no difference between application code and test code. If your tests lack in quality, they will hold back your effort. All right, so let's see what the hotspots brought us. We've already seen how the change frequencies alone help us narrow down the amount of code we need to consider. When we add the complexity dimension, we can narrow it down even more. And in general, I tend to find that the top hotspots rarely make up more than 3% of the code. Yet, we can be pretty confident that if we actually improve just those 3% of the code, we get a real return on that investment, both in terms of productivity and quality. And the reason I say quality is because hotspots are pretty good predictors of defects. All right, I'm going to return to the hotspots in a while. Before I do that, I want to talk about something else. I want to talk about the primary tool as software developers. And our primary tool isn't the compiler. It's not your IDE. It's not even Emacs or Vim. It's our brain. And I want to talk about our brain because your brain doesn't always work in your best interest. And I want to do this by taking a small poll. Please, everyone, think back to the last project you worked on, perhaps the project you work on right now. How many of you know where your hotspots are in that code? Come on, like not so many people. I can see around 20 hands. Great. So please keep your hand up if you're 100% certain. Oh, I see 2.5 hand. That's great. Yeah, you may well be right. You know your code. I don't know it. What I want us all to keep in the back of our head, though, is that if 50 years of psychological research has taught us something, it is that we humans, we can't really trust our own judgment. And to explain why, we need to talk about something else. Yes, that's right. We need to talk about gorillas. So this is one of my favorite experiments in psychology. It's a well-known experiment. You may have heard about it. Now, what researchers did here was that they recorded a video of 2 teams that played basketball with each other. And if you take part in that experiment, what will happen is that the researchers will sit you down in front of the video, and your task is to count the number of passes between players of the same team. Now, as you sit down to count the number of passes, something really interesting happens. A man dressed in a gorilla suit walks across the basketball field, stops right in front of you, turns towards you, and starts to beat on his chest. And then he walks off. After you've seen that video, the researchers will ask you, did you notice anything particular? And you would of course say that, yeah, I mean, a man dressed in a gorilla suit, that's at least a little bit odd, isn't it? And again, that's not what happened at all. It turned out that more than 50% of the participants failed to notice the gorilla. And this was a surprising finding. So what the researchers did was that they made a follow-up experiment. And this time they used some eye tracking devices. And it turned out that we humans, we fail to see the gorilla even when it's right in front of our eyes. Even when the image of the gorilla hits our retina, we fail to see it. And the reason for that is because you don't see with your eyes. You see with your brain. And in order to perceive something, we need to focus our attention on it. But your attention was directed to count the number of passes. And this experiment, after hearing about it, we really need to ask the question, if we humans are capable of missing something as obvious as a man dressed in a gorilla suit, what's the risk that we will miss the gorillas in our own code? And the human brain has other ways to get us into trouble. And I want to show you one more thing here. And this is about a thing that we humans are actually good at. Because we humans, we are great at rationalizing decisions and ideas that we don't even support ourselves. So this is a story about another experiment. If you take part in this experiment, what will happen is that you will be presented with two photos. Two photos of different faces, and your task is to select the face you find the most attractive. So you make your choice, and the researchers hand you a copy of that photo. Only they don't. They trick you. So they actually swap the photos, so you receive a copy of the photo that you didn't choose. And now they do something really, really evil. They ask you, could you please motivate your choice? Interesting. Let's think about that, right? So we sit there with a copy of a photo that we didn't choose and are now asked to motivate a choice that we didn't do. And again, if that would happen to you, I'm pretty sure you would say, this is not the photo I picked. Please give me the other one. And again, that's not what happened at all. In this case, 2/3 of the participants failed to notice the swap. And if you look at the original research, it includes part of the interviews where people start to motivate the choices that they didn't do. And it's so fascinating to read that, because it's really comedy gold. Because you will have, I remember a few cases. For example, there's this woman. She sits there with a photo and she says, I picked this photo because I just love the earrings. The photo that she picked don't show any earrings at all. And of course, you have this stereotypical overconfident man who sits there with a photo and says, I picked this one because I really prefer blondes. The photo he actually picked shows a dark-haired woman. Now, these are two examples on individual cognitive biases. They may get us into trouble, even in software projects. But we can do worse than that. If you want to see a real disaster, please try the following thing. Take a number of individuals, put them together, and call that a team. And to explain what I mean about that, we need to travel into some territory that looks a little bit unethical. But please relax, I promise to keep this nice. Now, how many of you have been given the advice that if you want to make an impact in a meeting, you should speak first? Not so many, just 1 or 2 hands, right. So, with that purpose, this is actually a good advice. Because it turns out, the first person to speak in a meeting will bias and influence the whole group. They will influence the whole discussion in that meeting. But there's an even sneakier way to manipulate people. And this is a phenomenon called vocal minorities. And vocal minorities are based upon the fact that we humans, when we hear an opinion repeated over and over again, we come to believe that that opinion is more popular and widespread than it actually is. And that's true even when it's the same person repeating the same opinion over and over again. So what this means is that if I want to manipulate you, all I have to do is to keep repeating stuff like, have you heard about Common Lisp? It's an amazing programming language. Have you seen the programming language Common Lisp? It's the best language ever. We need to use it all the time. Now, I try to be a nice person, so I will only manipulate you in a good way. Common Lisp is indeed great. But let's say it was the other way around. Let's say someone complained a lot. For example, have you seen that network module code? It's complete crap. That network module code, it makes me sick. We have to throw it away. It's useless. It's rubbish. If you hear an opinion like that repeated over and over again, how do you think it will influence your ability to perceive where your true hotspots are? And the reason I tell you all this is because I really, really, really want to make the point for my next slide. Because I think this is the most important thing I'm going to tell you today. Do use your intuition. Do use your expertise. And please make sure to support your decisions with data. And we've already seen an example on how hotspots can give us information that helps us make better decisions and prioritize code. And now I want to transition into another type of analysis that helps us get even more information. I want to uncover our change patterns in code. And I want to introduce this by talking about the cost of surprise. And I want to talk about surprise because surprise is one of the most expensive things you can put into a software architecture. And there are different kinds of surprise. I want to show you the first type of surprise by presenting what has to be my all-time favorite code. This code was part of the Apollo project. So this is the code that actually brought us to the moon. So please, take a few seconds and have a look at this beauty. In particular, focus on the comments. How many want to go to the moon on that code? I would argue that what you see here is likely to be a surprise to the end user. That's not the kind of surprise I want to talk about now. I want to talk about the potential surprise we as software developers leave behind for the poor maintenance programmer coming after us. And I want to show you how a concept called temporal coupling helps us detect those surprising patterns in our code. Now, temporal coupling is quite different from the way we typically talk about coupling. When we developers talk about coupling, we typically mean a dependency, right? I have a module here, it uses a module over here, they are coupled. Temporal coupling is different because temporal coupling isn't measured from code. Temporal coupling is measured from the evolution of your code, that is your version control history. So temporal coupling is about code that changes together over time. So you may have two or more modules that you keep changing in parallel like this over time, which means there has to be some kind of relationship between them. So let's try to be specific here, and I'm going to look at a few case studies so that you see a few examples on what temporal coupling may tell you. This is a case study from ASP.NET MVC. And ASP.NET MVC is a fascinating project in the sense that it actually has more test code than application code. There seems to be a huge investment in automating tests on ASP.NET. As a consequence, most of the temporal couples you would find look like this. You have a unit test, MVC option setup test, that changes together with the code under test. Now, this is not surprising. This is exactly what I would expect. In fact, if that dependency in time wasn't there, I would be worried, because it would probably mean that my unit tests aren't being kept up to date. So this is not a surprise. Let's look at something else. In the same code base, you will find two classes. One is called a script tag helper, and the other one is called a link tag helper. And if you look at the code, you will see that there's no direct dependency between those two files. Yet, they keep changing together in 89% of all commits. That's a really, really strong coupling in time. And when I find something surprising like that, I always look at the code. But today, I want to delegate that responsibility to you. So what will happen now is that I will show you a copy of the script tag helper, and I will put the link tag helper next to it. And your task is to see if you can spot some kind of subtle patterns between them. Are you ready? Here we go. Here's the script tag helper. Let's put the link tag helper next to it. Do you see any subtle patterns? Yeah, that's right. That's where I tend to find in a lot of cases a dear old friend. Copy-paste. But perhaps I'm being a little bit unfair to Microsoft here, because this is not really copy-paste. They've done something rare. They updated the copy-pasted property names. And they've done something even more rare. Believe it or not, but they've actually updated the copy-pasted documentation. So this is not copy-paste. This is copy-paste with a gold plating. And temporal coupling is great at discovering expensive change patterns like this. But we can do even more. We can use temporal coupling to analyze complete software architectures. And I'd like to give you an example using a microservice architecture. Why microservices? Because right now, microservices are all the rage. And that just means that tomorrow's legacy systems are going to be microservices. So let's stay a step ahead. This is what microservices look like in PowerPoint. In reality, they tend to look more like this. So we are developers. We have learned to avoid duplication. So of course, we encapsulate a shared communication library. And we notice some similar database access patterns. So let's introduce a shared database utilities library. And of course, we want to follow the recommendation of providing a shared service template so that our services behave in the same way. And of course, we want to make sure that our services are easy to consume. So let's add a client library to each one of them. Now, each one of those choices may well be good. The thing is, however, in a microservice architecture, loose coupling is king. The moment we start to couple different services to each other, we lose most of the advantages of a microservice architecture and are left with an excess mess of complexity. So if we have a guiding fundamental principle like loose coupling, why not supervise it? So what I suggest and what I recommend is to use temporal coupling, not between individual files, but between individual services. And what you want to do is to look out for patterns like this, where two or more services change together due to a shared dependency. Or even more important, when you have multiple services, where you have clusters of services that tend to change together in time like this. Which is something I've actually seen happen a few times when the same team is responsible for multiple services. It becomes so easy to start to send directed information. So if you do a temporal coupling analysis like this, you're able to get an early warning when things start to go wrong, when you break your fundamental principles, which means that you can react on time and prevent a lot of expensive surprises in the future. All right. Do you remember that I started to talk about social and organizational complexities? I would like to take it a step further and actually claim that most organizational problems are mistaken as technical issues. And I think the main reason for that is because if you look at the code, you cannot see any social information. There's no description of what kind of team that actually worked on that code and when they did that. And so I think that we really need a social view of our code base too. So let's have a look at that. This is an analysis of the implementation of the programming language Clojure. And this visualization is called fractal figures. And fractal figures works like this, that you consider each file as a box. And each programmer gets assigned a color. And the more that programmer has contributed to the code, the larger the area of the box. So if we add a color legend here, we actually get a useful communication tool. So let's say that we want to join the Clojure project and we want to make a contribution to the module over here, which is called evaluation. Now we see that all of that code is written by this one, Stuart Holloway. So if we have a question about evaluation, Stuart is probably the one to guide us. And of course, Stuart would also be an excellent candidate to review the changes we've done to that code. And of course, if we want to know something about Clojure in general, we see that most of the code seems to be written by that dark blue programmer. And that's someone named Rich Hickey. So if you have a question about Clojure in general, Rich Hickey may know a thing or two about it. But I think that fractal figures are really useful even without the color legend. And what you do in this case is that you look for patterns like this. What these patterns show you is that you have a module where 20 to 30 different developers need to work in parallel all the time. And this is important to detect because there's pretty good empirical research that shows you that the number of programmers behind a piece of code is one of the best predictors on the number of quality issues you will have in that code. And this also tells us something about our hotspots. So in my day job, I'm often hired to analyze large-scale code bases, and sometimes I come along code bases that's been around for a long, long time. 10 to 15-year-old code. And what I tend to find there is, again, most of the code is in the long tail, hasn't been touched in years. And then, of course, you have a number of really, really glowing hotspots where all the action seems to be. And when I look at that code, I see that that code has been a problem for years. It has probably cost a fortune to maintain it. So why haven't anyone improved that code? Why haven't that important piece of code where I actually work all the time, why haven't it been refactored? Do you know the reason why much existing code isn't improved? The reason is because their fractal figures look like this. So that means I cannot simply improve the code because I will have like 30 people who depend upon that code in their work all the time. And this is unfortunate because it leaves us in a situation that I call immutable design. And please trust me on this one. I love functional programming, but in this context there's nothing good with immutability at all. And I think it's ironic too, because the reason we cannot improve that code is because we are so many people working on it in parallel. And the reason we have to be so many people working on it is because we cannot improve the code. So the first step towards real improvement is to measure and understand what the problem actually is. Now, when we start to talk about the social metrics, I want us to also turn an eye towards our blind spots in code. And I want to introduce this with a case study of Paul Phillips. And this is interesting because this story reminds me a little bit about this morning's keynote. What happens when a core developer is fired or decides to leave themselves, as was the case here? So Paul Phillips worked on the implementation of Scala, the programming language, and he worked on Scala for 5 years. And during those 5 years, Paul was the top contributor to Scala. Now, 2.5 years ago, Paul Phillips made this video where he announces his decision to step back, to stop contributing to Scala. So I started to think, what's the consequence of a main developer that leaves? So I did an analysis of knowledge loss. And this analysis is done more than 2 years after Paul Phillips has actually left. So let's see how the knowledge loss looks like in Scala. So you see those red areas here? In this case, there aren't any hotspots. No, they represent abandoned code. That is, code that's written by a developer who's no longer part of the organization. And this is something you can use to reason about the knowledge distribution in your organization. So for example, you see there are a lot of red areas, a lot of abandoned code here in this large subsystem. That's something called a compiler, which may be important. You can also use this data a bit more proactively. And what you do in this case is that you look for patterns like this, where you have entire abandoned subsystems. So if you know that you plan to do some work there, use this information to schedule some additional time for learning, because it is a hugely increased risk to modify code that we no longer understand. All right, I've arrived at my final observation, because I'm pretty sure that to write maintainable code bases, we need to make it fun. At Ampere, we use Clojure for most of our work. And I often get the question, why did you choose Clojure? And I could tell people things like, yeah, you know, we do data analysis, and Clojure is a great tool for data analysis, which it is. However, that's not the reason we choose Clojure at all. In fact, it wasn't even a technical reason. The reason I picked Clojure was because it looked fun. I wanted to learn the language. And I think that fun is a much underestimated driver of design. In fact, fun is a much underestimated motivator in the software industry, because fun is virtually a guarantee that things get done. So if you work on a large legacy system, remember to keep the fun in it. And I mean, even if you're locked down in a choice of languages or technologies, there's always a lot of supporting code to write. So the next time you face a mundane, boring, repetitive task, automate it, and automate it in a language of your choice, something you're excited about. Turn a boring, repetitive task into a learning experiment, and your code will thank you for it. So, I'm almost done now. If you want to read more about this, I blog a lot about it, different case studies, and of course I have my whole book, Your Code as a Crime Scene, where I go into this stuff in more detail, and where I also look at some of the empirical research behind it. And I'm going to leave time for questions now, but before I do that, I want to take this opportunity and say thanks a lot for listening to me, and please remember that Common Lisp is a great language. Thanks. Thanks a lot. So, do you have any questions? Yeah, so the question is, do I have any tools to do that analysis? And the answer is, yes, I do. And I actually had to write my own tools, because I started out to do this stuff as part of my own day job as a consultant 5-6 years ago. And at that time, there weren't any tools available. So I started to play around with it. And when I wrote my book, I also published a small open source tool called CodeMath that you can have a look at. It's available for free. You can just go to my webpage and you will find a link to it. And after that, I left my consultancy career to focus on building tools and improving them, because it turns out there's actually a lot of work and research necessary to do that. So if you want to have a look at the tools that I use to do these case studies, have a look at Ampere. And what I work on right now is to provide the tools as a cloud-based service. So if you want to be part of the preview, I really hope it's going to launch in a few weeks. Sign up at CodeScene.io, it's free. And I will be excited to have you there and get your feedback.
You mentioned a few functional languages. Let's say that someone wants to learn something new.
Yeah.
Would you recommend?
Oh, so you mean a particular language? Yeah. Yeah. So the question is, if you want to learn something new and you want to learn a functional language, which language should I choose? This is so controversial, actually. This is almost a religious topic. Let me tell you, I actually have a traumatic experience, right? I was a C++ developer for 10 years. Those are 10 years I'll never get back. So, you know, I avoid everything that smells over complexity and multi-paradigm. So that means, sorry, Scala, you're not going to cut it. I want to focus on something that has few and relatively simple concepts that challenges my current way of thinking. And this, I think, is the best way to learn, to pick something that you're not comfortable with at all. And Common Lisp is great. Common Lisp is actually... I just love it. And it's so good. And the thing is with Common Lisp, it's not necessarily a functional language. Common Lisp actually has the best object system I've ever seen. So even if you're interested in just becoming a better object-oriented programming, have a look at the Common Lisp object system. It's a completely different way of thinking about object orientation. And Clojure is great because it's, I would say it's more practical than, Common Lisp is also a practical language, right? But Clojure is more accessible because you have built on the whole power and ecosystem of the JVM. So you have a lot of supporting libraries and tools. So that's the main reason I picked that over Common Lisp. And then you also have things like Erlang, which I think is great. If you do some kind of soft real-time systems, distributed systems, which I think most people do these days, have a look at Erlang. It's a really fun language. It's really great, and it's also really, really simple. There are actually few concepts to understand. You're able to learn it in a few days. Then you just need 5 years to master it.
Are these tools for particular SEM, like
Very good question. So in my book, I actually discuss how we do this on Git, Subversion, Mercurial, and so on. But the tools I build now, they only support Git. And that actually sounds a bit more limiting than it actually is. Because it turns out you can convert most version control systems into a Git repository and analyze that. So I've done analysis on Subversion and TFS and Mercurial too. And it works pretty well. You tend to, TFS may be the most problematic of those, but because it tends to encourage a workflow where you actually lose a lot of data. But the technical analysis turn out really fine on that.
Have you ever had a team continuously use this kind of analysis, like doing checkups or sanity checks every month or 2 months, or is it like a one-off analysis that you do usually?
So great question. So basically, is how often do you do an analysis like this? And the answer is, this is something I would recommend that you do every day. You start out with a bigger, more in-depth analysis, but then it turns out that a lot of those warning signs that you look for, those patterns you look for, those are possible to automate. And when things start to go wrong, you want to know it immediately. So I would say run it once every day. More often than that is perhaps not necessarily, because it doesn't change at that rapid rate. And I would also recommend that you bring data like that, analysis results like that, into your retrospectives. You know, when you have all your stories and features you worked on fresh in your head, then you can see how they actually impacted your code base. Because I find that code is often sadly absent from our retrospective, and it's actually the most important part. Hope that answered your question. So, do these techniques require sophisticated machine learning techniques? Some of them. What I've shown you now is only actually, it's a small subset of everything I do. And I blog more about it, and there is an ongoing blog series at Ampere that I write, and where I show a bit of more things you can do with this kind of data. So I would say like 80% of that stuff doesn't require machine learning. I do use machine learning a lot, but most of it is based on, you need a solid foundation in statistics, basically. And then there's also the more engineering problem. How do you work with data that's not always perfect? For example, one interesting thing with version control data is that we need to pick out the actual source code, the historic source code, because we want to see trends in time. For example, has this hotspot, has it increased in complexity and so on? Is it any particular part of that file that deviates? In order to do that, you need to parse the source code. The thing is that it sometimes happens that people check in code that isn't even valid, that doesn't compile. There's no way to detecting that. You have to pick it out, and you need to kind of handle that the data is imperfect. So it's quite challenging from an engineering perspective, but it's also a lot of fun, which is why I do it. One final question. Yes?
Your data is not the pain of any commit. Is it any problem? So if I have one commit every 3 or 4 months and it's 3-day working of one bug fix, that's maybe a hotspot, but not in your data.
Cool. So the question is, basically, are there individual differences in commit style? So some person may commit like 5 times each hour. Another one works 3 days on a single feature before they commit it. The thing is, yes, if you have those extremes, it will bias the results, obviously. So the first thing I recommend is to try to agree upon a shared commit style. It's really helpful, not only for that, but for a lot of other things. The other thing you can do is that you can use an alternative metric, something called code churn. So instead of looking at change frequencies, you look at the amount of code that you have actually changed. So you get a percentage that you have changed, like, I don't know, 70% of that module over the past weeks. And this erases all the individual differences in commit styles, because now it doesn't matter if you've done 10 commits or 2,000. You just look at the total amount of changed code. So that's a way around that bias.
But I mean, if it's only on some files, I normally commit every hour.
Yeah.
And on some files, because it's so complex, I need 3 days for a bug fix, for example, and only have
Oh,
one
yeah.
commit.
Yeah.
So then
Yeah, so I understand. Yeah, I think I understand what you mean. Yeah. So the thing is, that may of course happen, that you have code that's so complicated you don't have to work with it often, but sometimes you have to go into it, and it may be a huge problem just to understand what it does and do the fix. And yes, you have spent a lot of time on it, but it won't show up as a hotspot. That's right. The thing is here, all these techniques, they never ever provides absolute truths. They never do that. What they do is they calculate probabilities. So this is something that it doesn't replace something. It's something that complements your expertise. So this is something that you use to direct your expertise to where it's likely to be needed the most. But it doesn't replace your expertise. All right, I will be hanging around for the rest of the conference, and I'll be more than happy to take more questions. Just approach me and I'll be more than happy to talk with you. I also want to say I have a beautiful batch of Codes or Cramps and stickers, so if you want one, come and grab them. Once again, thanks a lot for listening to me. Thanks.